So what could be the inner? Very good. So now I got one number here. One number. 1 over x. Any questions? Any questions? I like to look at problems 43 through 50 and then move on. And we can look at a word problem here. So 43 through 50, and I'll let you choose if you want. We're given the information though, and I have to copy the information. We are given that f of -1 is 4, f of 0 is 5, f of 2 is 7, f of 7 is 1, g of -1 is -4, g of 0 is -3, g of 2 is -1, and g of 7 is 4. 43 through 50 on page 718. 43. This is given to us. These are all given. We have not chosen the problem yet. You want me to choose? Or you will choose? Okay, I'll choose 49. F divided by g of -1. By definition, this represents what? F of divided by g of -1. Excellent. Now let's look at the information we are given and come up with f of -1. How much is that? Very good. And g of -1. So the answer simplified form is -1. Good. Let's look at f come g of 2. That is 45. F come g of 2. By definition, this represents f of g of 2. And I have to start with the inner function. What is g of 2? What does g of 2 equal to? Right. So then I'm asked to really find f of -1. And how much is f of -1 then? 4. Very good. Now let's look at a word problem in which algebra functions is used. Okay, let's say 54. Yes. Becky, go ahead. Yes? You do or you don't? Did you say yes or you said no? Which one? Yes, because we have g of 2, which is -1. So we replace g of 2 by -1, and then f of -1 is 4. Better? Yes. Perfect. Okay, 54. Suppose that revenue R of x for x units of a product can be described by 25x revenue. And the cost C of x can be described by 50 plus x squared plus 4x. Cost. Find the profit. P of x. Profit. This is a typical problem for algebra functions. So we're given the revenue, we're given the cost, and now we're asked to find the profit. So we know that the profit always equals money coming in minus money going out. Revenue is coming in from the sale of whatever, and the cost is going out. So this is the revenue minus the cost. This is a typical situation for subtracting two functions. So then I copy the revenue, which is 25x. Carefully I put minus, in parentheses, 50 plus x squared plus 4x, because everything has to be subtracted. Each and every piece from the cost, not just one term. Any questions? So I distribute 25x minus 50 minus x squared minus 4x. And yes, I have to write it in descending order. Negative x squared plus 21x minus 50. This will be the expression for the revenue. Forgive me, for the profit. Any questions? Okay. I think we're ready to move on to section 12.2, inverse functions. Okay, so from the list, if you want to go back to the list for a second, you don't have to, I will. So this is our third topic. So these are done, and we are here with the inverse functions. Okay. Let's look at three situations. When we first talked about functions, we looked at three different situations. I'm going to repeat them here. This is one. You can put numbers here if you want, whatever number you decide, it doesn't matter. This was one option. Here was the second option. And here's the third option. That's all we had. Just these three. Okay. Okay. Now, question, is this a function? Yes. Each x corresponds to one y, correct? Good. Now, imagine that I'm here, and I want to create a function going back. In other words, now this becomes a domain, and this becomes a range. Can I create a function going backwards? This back to this back to this, and this back to this. Yes. Is this a function? Yes. Awesome. Let's go here. Is this a function? Yes. Yes. Each x corresponds to one y. Each x corresponds to one y. Each x corresponds to one y. But now, I'm here, and I want to create a function going backwards. Can I? No. No. So this is a function, but it's not 1 to 1. So 1 to 1 means one y corresponds to one x as well. The function requires each x to correspond to only one y, but even going back, one y corresponds to one x. This function is 1 to 1. What about this? Is this a function? We have nothing to discuss here then. Not a function. So these were the three options that we had a long time ago in chapter 2. Good. So now I know that some functions are 1 to 1 and some functions are not 1 to 1. Let's look at a few graphs. And you can ask me, and what is so fancy about being 1 to 1 for a function? Very fancy. I'll explain in a minute. We graphed all these four functions in the past. Can anyone identify the first one? Quadratic, excellent. Is the quadratic function one-to-one? Remember, one more time. Each y corresponds to one x. For this y value, how many x values do I get? Exactly. Is this one-to-one? No. Not one-to-one. What function is this? Absolute value. Excellent. By the horizontal line test, is this function one-to-one? No. What function is this? The one that no one really likes. No one fell in love with the square root. I don't know why. Is by the horizontal line test, is the square root one-to-one? Yes. One-to-one by the horizontal line test. Last one. What function is this? Right. Is the linear function one-to-one? Yes. One-to-one. Okay. So you probably figured out by now because, yes, Becky? I'm sorry? The top right, absolute value. Sorry, absolute value. So you probably figured out where am I getting to. Because I was asking if I want to go back, can I create a function? So this is how we determine or how we create the inverse function. But the function must be one-to-one to have an inverse function. If it's not one-to-one, it will have an inverse, but that's not going to be a function. So here's our next note. Only one-to-one functions have exactly inverse functions. Only one-to-one functions have inverse functions. Here's the notation. You may not like it, but that's what it is. So let's say I apply x to 2 and I apply f to x equals 2, and let's say I get y equals 3. What is the ordered pair for function f? Of course. But now I want to go backwards and I want to create a function that is the inverse function of function f. Here's the notation. And no, it does not mean 1 over f. It's read f inverse. It's just a notation. F inverse of x. Yes, Becky? By the horizontal line test, the square root is 1-to-1. Good. Can anyone give us the ordered pair now for f inverse? Exactly. For the inverse function to reverse the operation of f, it has to be applied to 3, and it must result, or it must have the output of 2. Otherwise, the function, it will not be the inverse function. So what can you say about the domain of the inverse function? It's the range of the function. What can you say about the range of the inverse function? So these are for the inverse function. What will you say about the range of the inverse function? It must be domain of f. Excellent. Oh, yes, Becky? Where are you? Okay, on page 728, let's see how we find the inverse function. 4-step procedure for finding F inverse. 4-step procedure for finding F inverse. So please give me a linear function because we know it's one-to-one and we know it's going to have an inverse function. Give me any linear function you can think of. Very good. You said 2 or 3. I wrote 3. It's okay. Step number 1. Yes? F inverse. So an ordered pair is trigonometry. Step 1. Replace f of x by y. First of all, am I allowed to do that? Can I ever replace f of x by y? They are the same. Good. So then y equals 3x plus 3. In step 2, interchange x and y. And you can say, wait a minute, that we have never seen before. But here's why. 3 is a y value for f. But what kind of value will be for f inverse? It would be its x. That's why I'm allowed to interchange them. 3 is the y value for f, but 3 is the x value for f inverse. So that's the reason why we interchange x and y. Where I see y, I write x. Where I see x, I write y. Step 3. Solve for, what do you think we're solving for? The new function, which must be y. Solve for y. So how do I solve this equation for y? I subtract 3 and divide by 3. So y equals x minus 3 over 3. What do you think will be the final step? I'll start the first word. Replace exactly. Replace y by the notation f inverse of x. Perfect. Awesome. Okay, so let's find another function or choose another function and try to find its inverse function. Let's say 37. On page 728, we have f of x equals 5 divided by 3x plus 1. We are told this is a one-to-one function. So no dispute there. We don't have to do anything. We don't have to graph. We don't have to perform any operations. We are told the function is one-to-one. Awesome. So what do I do now? First step. Exactly. That's our first step. We replace f of x by y. Second step. Exactly. Excellent. So y equals 5 over 3x plus 1, and then x equals 5 over 3y plus 1. We know what we did in the previous chapter. What kind of equation is this? If you notice that you can do this. How did we call this equation? PR O P proportion. What do we do in a proportion, and only in a proportion? Cross multiply. Yes, you can multiply both sides by 3y plus 1 if that's what you want. It's the same thing. So x, quantity, 3y plus 1 equals 5. What are we solving for? Let's not forget the target. We're solving for y. Excellent. So then what do I have to do? You have two options. You either distribute or you get rid of it. You want to distribute? Okay, fine. So 3xy plus x equals 5. Then 3x equals negative x plus 5. 3xy, I'm sorry. So therefore, y must equal negative x plus 5 over 3x. This is our F inverse. Negative x plus 5 over 3x. Of course, we should have stated a restriction, and we have to state a restriction for both of them. So obviously here x cannot be perfect. And here, they should have stated that in the problem. X cannot equal 1/3. Good. Let's think of the following experiment. Let's say you have X dollars in your pocket. And I'm giving you 10. What function did we just create? You have in your pocket an unknown number of dollars, unknown amount, but I'm giving you 10. So we created a function. What is the function we just created? X plus 10, right? You have X in your pocket. I'm giving you $10. We created a function depending on what you have. If you have $5, then now you have 15. If you have $0, now you have 10. If you have 20, now you have 30, right? So we created a function. The amount you have in your pocket plus 10, correct? Okay. Now, 5 seconds later, I come back and say, give me my money back. We created another function. What is that function? X minus 10, right? So I created X plus 10, and then I created X minus 10. After this procedure of giving you 10 and taking it back away from you, how much money do you still have? X. Right. So are these two operations inverses of each other? Giving you 10 and taking it away, I created two functions that are inverses of each other, right? Giving you 10 and taking it away from you, there are two functions that are inverses of each other. So if I apply two inverse functions in any direction, I can say give me 10 and I'll give it back. Or I can say here's 10 and give it back to me. So it doesn't matter if I apply the difference first and then the sum, or I apply the sum and then the difference. But when I apply two inverse functions, first I'm adding 10 and then subtracting, or I'm subtracting 10 and I'm adding 10. What happens to x? The answer is nothing. So here's my question to you. Every time we create, for whatever reason, this function composition and this function composition, these are two inverses of each other, two inverse functions. What do I always get? If the functions are inverses of each other, they have to cancel their effect on x. So if I apply this or this, what do I always get? Indeed. This is so-called the property of inverse functions. The property of inverse functions. This will never happen unless these two are inverses of each other. I could get x squared or x plus 5 over 3 or negative 5x. But if I get plain x, these must be inverses of each other. Whatever I apply to x, the other one will cancel. Okay? So let's say we are given two functions. Let's look at 48. We are given f of x, which is 3x minus 10, and we are given g of x, which is x plus 10 over 3. We're asked in this problem, show whether they are inverses of each other. What do I have to do? Yes, you can say, I can take this and find its inverse. And if I get 3x minus 10, it's obvious. They are inverses of each other. However, I would like to use the property of inverse functions to show whether they are inverses of each other. What will I do? I will find f come g. I will find g come f. And if in both cases the answer is plain x, I conclude that f and g must be inverses of each other. Now, if for the first one I get x plus 2, should I bother with the second one? No. If the first one is x, do you think that the second one will be x? But I have to show it. So f come g. F of g of x is f of x plus 10 divided by 3. I look at f now. And f says 3 times whatever minus 10. 3 times whatever minus 10. What will you do first? And you will say, get rid of 3, because you can. We learned that. They're factors. And then I'm left with x plus 10 minus 10. And the answer is x. I know that the other one has to be x as well, but I still have to find it. So this is g of f of x. Any questions before we continue? Any questions? Ready? So g of f of x will be g of 3x minus 10. And g says whatever plus 10 over 3. Okay, whatever plus 10 over 3. These two will go away, combining like terms. 3x over 3, I know I'm allowed to simplify factors. So the answer is x. So what do we conclude about f and g then? Therefore, by the property of inverse functions, f and g are inverses of each other. Now, if you wanted to, you could go back and say, oh, I don't need this because this is F inverse. Or the other way around. Say, oh, I don't need this because that's G inverse. They're inverses of each other. I would like to graph them on the same coordinate system. And you'll see what happens. Something very interesting. So f of x, 3x minus 10, and g of x, or f inverse, x plus 10 over 3. So now I want to graph f of x and g of x on the same coordinate system. Let's do that. Ready? Okay, so let's start with 3x minus 10. So y equals 3x minus 10. Get rid of this one. When x is 0, because this is a line, y equals negative 10. So the first ordered pair is 0, comma, negative 10. Okay? The other one, when y is 0, I have to move 10 to the other side. So x equals 10/3. So the other ordered pair is 10/3, comma, 0. You can say kind of difficult, yes, a little bit, to plot 10/3, but that's okay. Zero, comma, negative 10 is here. Yes, Becky? Yes. This one? Okay, very good. And 10/3 is a little bit more than 3. I'm going to say right here. I'm going to connect the 2 points and extend the line. And this is f of x, 3x minus 10. I will not find 2 ordered pairs for the other one because you will give me 2 ordered pairs with no calculations. Can anyone give us 2 ordered pairs that will help us graph the inverse function? Indeed, the reflection right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This point is reflected here. Excellent. By reversing the coordinates. Excellent. And the other one? 0, 10/3. Connect and extend the line. So this is f inverse of x, which is x plus 10 divided by 3. Oops. Good. Now I would like you to notice a very important property. My graph is not perfect, but this has to overlap this, and this has to overlap this. And this is a line. Can anyone give us this line? It has to pass through here, and it has to the origin, and it has to pass through the point where they are the same. which line is this? And then we will write a note. The graphs of f of x and f inverse of x are always symmetric with respect to the line, and you'll tell me the line. The simplest possible linear equation. It passes to this point, 0, 0, and it passes to this point where there is no reflection. 5, 5, 2, 2, 3, 3, 9, 9, 10, 10. Exactly. In other words, y equals x, where x and y are the same. So note, the graphs of f of x and f inverse are always symmetric with respect to the line y equals x. Any questions? Any questions? Okay, what is left? We're done for today. But what is left from this chapter? We're going to talk about exponential and log functions, equations, and